Yo, what's up everyone? Welcome to Kinetics Part 3. Today we're going to go over collision theory and reaction mechanisms. So what is collision theory? Well, collision theory tells us that the rate of a reaction is going to be dependent on the number or the force of collisions. And it has three little postulates, and to kind of make an analogy between it, I want to use this pen, or this highlighter really. Imagine the highlighter cap and the highlighter itself are reactants, and the product would be like the capped highlighter. So let's look through the three postulates and see how they relate to this analogy right here. First of all, reacting particles must collide. So in order for us to create this capped highlighter, these need to collide at some time. If they never collide, then you can never have the product. This can never occur if these two reactants never collide. The second one tells us that reacting particles must collide with proper orientation. So if I do make them collide, if I make them collide like this, they're not going to create a capped highlighter because they're facing the wrong way. The proper orientation would be if the cap was like this and the pen was like this. And then if they collide, then they would create the capped highlighter, which is the product that we want. Number 3, reacting particles must collide with sufficient energy. If I make them have proper orientation like this, but I don't provide enough energy that they only go halfway, then they're not going to create the product because they haven't collided with sufficient energy. If I make them go really close over here, they still haven't made the capped highlighter because if I turn it around, it just falls off. There needs to be a proper amount of energy, they must collide, and they must have proper orientation. These three postulates are really important, but really they boil down to this general rule. And that says that the number of collisions, an increase in the number of collisions, is going to increase the reaction rate. And we can see this in multiple things, like an increase in temperature, or the increase in the number of particles, or the increase in reactant surface area is going to increase the number of collisions, and therefore all these things are going to increase the reaction rate. So really, a big fundamental takeaway of collision theory is this. An increase in the number of collisions is going to increase the reaction rate. And intuitively, that makes sense, right? If you have more collisions, then you're more likely to have collisions that have proper orientation and sufficient energy. I want to go into depth into two of these little postulates, starting with the third one, which tells us that reacting particles must collide with sufficient energy. To see like how much energy you really need, you have to look at something called an energy diagram. And in an energy diagram, on the y-axis, you have potential energy, and on the x-axis, you have reaction coordinate. And reaction coordinate just means, the progression of a reaction over time. And potential energy just means potential energy. And so if you were to plot reactants and products, you can see at the start, you're going to have just reactants, and all the way at the end of the reaction coordinate, you're going to have products. And in this case, the reactants are going to be below the products, and that just means that this reaction is going to be exothermic. Essentially, if you look at the progression of potential energy from reactants to products, it would look something like this. And that top little bit is called the activated complex, or the transition state. And essentially, the difference in the transition state and the reactants is what you call the activation energy. So it's signified by EA. And the activation energy represents how much energy the reactants must have in order to be able to go past this little bump and become products. So if they have that amount of energy or more energy, reactants can turn into products. But if they have less energy, then they are not going to turn into products. And in this case, we're told that the activated complex is at 25 kilojoules per mole, and the reactants are at 5 kilojoules per mole. So our activation energy would be 20 kilojoules per mole. So yeah, reacting particles must collide with sufficient energy. The next one I want to go over is number 1, and that says that reacting particles must collide. And that's really important because there are going to be different types of reactions based on how many particles collide. So there are particles where just one molecule collides, and that seems kind of unintuitive, but it goes a bit more complicated than just one particle colliding. But just don't worry about that. We say when one particle produces a product, we call that a unimolecular reaction. And similarly, if we have two particles colliding, we call that a bimolecular reaction. And if we have 3 or more, it's going to be called a termolecular reaction. The thing about this is that the relative abundance of these types of reactions are going to be very different. So think about, analogize yourself in a room blindfolded with 30 other people. A lot of the times you're going to have these bimolecular collisions. So you and someone else are going to collide, but how many times are 3 people going to collide at the exact same time? Well, it's not a lot. In fact, for around 1,000 bimolecular reactions, there's going to be about 1 termolecular reaction. So when you see more than 2 particles colliding at the same time, then that means it's quite unlikely to happen in just one fell swoop. So something like this reaction right here where 2A plus 2B produces C plus 2D, well, you wouldn't actually have this reaction happening all at once because the 2A and the 2B are going to signify 4 particles. And the likelihood of 4 particles colliding at the exact same time is really low. What you have instead is something called a reaction mechanism. So these are going to be a process by which a reaction occurs. For this particular reaction, you might have something like this, where 2A first produces E, and then E plus B produces F plus D, and then F plus B produces C plus D. And you can see how this adds up. So let's just do that really quickly. The E that's produced here is canceled out by the E that's required here. The F that's produced here is canceled by that one. And then I think that's it. So we can add these all up. That's 2A plus 2B produces C plus 2D. And that's exactly what our final reaction is. An important thing about reaction mechanisms is that they're created. They're not really, we don't really know them for sure. We create them to kind of explain how a reaction occurs. Now, these reactions, these little mini reactions, are what we call elementary reactions. So elementary reactions are part of a reaction that occurs in one step. These are going to occur in one step because, again, we have bimolecular reaction. We have a we have a bi. And you're not having those termolecular reactions that would be very, very uncommon. A special thing about elementary reactions is that the rate law of elementary reactions can be determined from their stoichiometric coefficients. So remember, the overall reaction rate law, the overall rate law cannot be determined from the stoichiometric coefficients, but if we have an elementary reaction, then it can be determined from their stoichiometric coefficients. So if we look at this elementary reaction over here, C plus D, that its rate law would be rate equals K times the concentration of F raised to the first power times the concentration of B raised to the first power, because again the stoichiometric coefficients of F and B are going to be 1 each. Now let me introduce a few more vocabulary words. So let's take a look at this reaction mechanism where A plus B produces C, and then C plus D produces B plus E. And then the overall reaction is A plus D produces E. So you see kind of an interesting thing here where where a product is produced and then that same product is used immediately afterwards. That's what we call an intermediate. Intermediates are substances formed in one reaction and used up in a subsequent one. And kind of on the opposite side, if you look at B over here, it's used up in one reaction and then produced again in a subsequent one. These are what we call catalysts. So catalysts are substances used in one reaction and reformed in a subsequent one. Okay, when you're going to be given a reaction mechanism, you're also usually told one more other thing. And that's whether or not the reaction is going to be fast or slow. Now, the rate of the overall reaction is going to be the same rate as the slowest reaction. And that kind of makes sense. If you think about an assembly line, the speed of the entire process is going to be as fast as its slowest worker. And so that tells us something special. That tells us that the rate of the overall reaction is going to be the same as the rate of the slowest elementary step. And remember, we can determine the rate law of elementary steps using their stoichiometric coefficients. So of the rate law of this overall of this overall reaction is going to be equal to the rate law of this little elementary reaction right here. And so rate would equal K times the concentration of NO2Cl times Cl. There is a problem with this though, and it's that one of the things that we have in our rate law is an intermediate. Intermediates and catalysts cannot be included in your rate law. And so how would we get rid of this CL that we have right here? Well, usually you're going to be given a fast equilibrium step as well. And now that little symbol right there is what represents equilibrium, and we're told that it's fast. The important thing about the equilibrium is that really there are two reactions. They're NO2Cl turning into NO2 plus Cl, and then it's NO2 plus Cl turning back into NO2Cl. So these are reversible reactions. And the important thing about equilibrium is that when they are at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So the rate of this reaction right here, the forward reaction, sorry, my pen's not working. The rate of this forward reaction is going to be K times NO2Cl. And the rate of this one right here is going to be equal K to the, actually I should include subscripts to represent that these K's are different. So K negative 1 is going to be equal NO2 times Cl. And now we can kind of set these equal to each other. So K1 times NO2Cl equals K minus 1 times NO2 times Cl. We can isolate the concentration of Cl. Okay, I cleared up some of the clutter, and now if we isolate for Cl, that's just going to be K1 over K minus 1, and then NO2Cl, and then NO2. And so what we can do is now we can substitute that into the Cl that we have over here. And essentially, we're going to be multiplying all the K values. And so we can just say that entire new K value is just going to be K. And so that K is going to be multiplied by NO2Cl that we have over here. And then this little fraction that we have over here. So NO2Cl over NO2. And that would be our final rate expression. All right, so again, this would be our cleaned up little rate law of the overall reaction. And so what we basically did was we took the slow elementary step, and then there was a intermediate in there, so we had to replace that with some of the other stuff in the fast reaction. And this is our overall rate law. And so let's do a bit more practice with problems from the real test. So nitric oxide reacts with hydrogen according to the following equation. A possible mechanism for this reaction is blah, blah, blah. What rate law is implied by this mechanism? So again, we start off with with the rate law of the slow elementary step. So the rate law of the slow elementary step would be K. Let me just do S, represent slow, and then N2O2 times H2. And that would be the rate of the slow elementary step. But you'll notice that we have a intermediate here, the N2O2. And so what we can do is we can look at the fast equilibrium. And so that the fast equilibrium tells us that the rate of the forward reaction, which is going to be K1 times NO squared, is going to equal the rate of the reverse reaction, which is going to be K minus 1 times N2O2. So if we isolate for N2O2, then it's going to be K1 times NO squared over K minus 1. And what we can do now is that we can substitute this value for the N2O2 over here. Okay, so Ks times the K1 times NO squared over K minus 1 times H2. And essentially, all these K values, they're going to multiply and divide. And so we can say that their final value is just going to be standard K. So at the end, what we have is K times NO squared times the concentration of H2. And that's going to be the rate. And that is answer choice B. And that is the correct answer. So again, learning that the slow reaction, the slow elementary step is going to be the rate law of the entire reaction. And then solving out for any intermediates or any catalysts using the fast equilibrium reaction. Let's move on. The formation of NOBr, 2NO, blah, 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 is studied and the following mechanism is proposed. What rate law is predicted by the mechanism? So again, let's start with the slow step. So our rate of the slow step is going to equal Ks times NO times NOBr2. But again, NOBr2 is going to be an intermediate. Sorry, let me move that out of the way. The NOBr2 is going to be an intermediate. So we need to get rid of that using our equilibrium step. So K1, this is going to be the rate of our forward reaction. So that's going to be NO times BR2. That's going to equal the rate of the reverse reaction. So K minus 1 times NOBr2. And if we solve for NOBr2, we get K1 over K minus 1 times NO times Br2. And that's going to equal the concentration of NOBr2. Now what we do here is we just substitute that into the rate law of our slow step. And so all that K is going to cancel out to just normal K. And now we can multiply. Well, we have NO once, and we also have NO from here, NO, and then BR2. So K is going to equal, the rate is going to equal KNO squared times BR2. And that's our rate. So that is going to be answer choice B. And that is the correct answer. I've said it like 5 times over, again, using our slow step and then canceling out the intermediate, so the catalyst using our fast equilibrium step. I have one more. This is the last one. It's the same question, or the same setup for the question, but in this case, it asks us in the reaction, NOBr2 is best described as, well, NOBr2 is produced in one reaction and then used up in the subsequent one, and that is what we call an intermediate. And that is answer choice A. Alright, that's all I have for this lesson. Again, slow step, and then take out the intermediates of the catalyst using the fast equilibrium step. That's usually going to be the setup for most of these reaction mechanism questions. You just need to learn how to identify them, and then just knowing the process to solve it, and of course just using that process to get the right answer. That's all I have. I hope you learned something, and I'll see you later.